Welcome to Chapter 21, Cost Minimization. In the previous chapter on profit maximization, when we were trying to model firm behavior, what we presumed is that firms chose the quantity of inputs that they used directly. So if a firm was using labor and capital, we suppose that they chose the quantity of capital and labor that they used to maximize profit and were unconcerned with the quantity of output that they produced. From your prerequisite course in Intro Micro, we model firm behavior as the firm chose the profit maximizing quantity of output. And to implement that, we actually have to be a little bit more careful. We have to do that to be theoretically sound in a two-step process. We have to first ensure that at each quantity of output, the firm is producing output in the cost minimizing way possible. Then, contingent upon that, we can choose the profit maximizing quantity of output. I refer to that tongue-in-cheek as the Texas two-step. Cost minimization, what we do is the firm chooses the quantities of factor 1 and factor 2 to minimize their total cost. Total costs would be the amount that they spend on good 1, which is the price, the factor price, omega 1, for each unit of factor 1 times the quantity they use, plus total expenditure on factor 2, subject to producing the desired level of output. In other words, they choose the cheapest way of producing the output that they want, given their technology constraint. The technology constraint we illustrated back in Chapter 19 as an isoquant. You remember the isoquant, iso meaning same, quant, it was combinations of the inputs that produce the same quantity of output. In this chapter, we're going to introduce iso cost lines. That would be combinations of inputs that cost the same amount of money. As you think about that definition, it sounds surprisingly like a budget line, which we developed in Chapter 2 of this text. And in fact, you would be correct. An iso cost line really is a budget line by another name. So total cost is equal to the dollars that the firm spends on factor 1 plus what they spend on factor 2. Now, to plot an isoquant and an iso cost in the same graph, you remember isoquants were plotted with the factors x1 and x2 on each axis. x1 was the horizontal variable, x2 was the vertical variable. So we need to rearrange the equation for this iso cost line to place x2 as the vertical variable, x1 is the horizontal variable. We'll do that just like we did with budget equations back in Chapter 2. And what we find is that the slope of an iso cost line is the ratio of the factor prices, omega 1 and omega 2. Now, the first example we have of this would be of perfect complements. So let the production function be illustrated as minima of x1, x2. That specifies that this firm needs equal amounts of x1 and x2 to produce output. If we want to illustrate this for an isoquant where the firm is producing 10 units of output, I claim it's quite evident that the firm needs 10 units of factor 1 and 10 units of factor 2 to produce an output of 10. Given the factor prices of 2 and 1, the total cost to the firm of producing 10 units of output is going to be $30. Now, since we're choosing the cost minimizing quantity of factor 1 and factor 2 to produce a given level of output, much like in the theory of the consumer, we derived demand functions. Those were closed form solutions that showed the quantity of good that the consumer would purchase to maximize utility subject to a budget constraint. In this, the theory of the firm section of the course, we're going to derive factor demand functions. Factor demand functions will show me what quantity of factor 1 and factor 2 the firm purchases to produce a desired level of output, Y, minimizing costs. So the way I would read this, the first one, x1 as a function of omega 1, omega 2, and y, what that says in words is that the quantity of factor 1 that this firm purchases, given the prices, and that they want to produce a level of output y, is y. Right? So in the numeric example, we wanted to produce an output of 10. The firm needed 10 units of x1. In general, if we want to produce y units of output, we need y units of factor 1 and of factor 2. If the two factors are perfect substitutes, we return to the world of Shirley Sixpack and Lorraine Quiche from the theory of the consumer. You remember that if goods were perfect substitutes, a consumer would choose to consume all of one good and none of the other, unless the budget line was on top of the indifference curve. Firms behave in much the same way. The cost minimizing choice of inputs will be to use all of one factor and none of the other, unless the isocost line is on top of the isoquant. So in this numeric example, what if we wanted to produce 30 units of output? 30 units of output can be produced, given this production function, by using either 7.5 units of good 1 at a total cost of $15, or by using 10 units of factor 2 at a total cost of $10. So quite evidently, this firm will want to produce output using factor 2 only. We can specify the firm's factor demand for x2 using a case statement, much like we did back in the theory of the consumer. If the firm wishes to produce y units of output, given this technology, they are going to need y over 3 units of factor 2, given production with factor 2 is cheaper. So this expression that I have at the far right says it's comparing the dollar cost of producing y units of output using factor 2 and y units of output using factor 1. So if production with y2 is cheaper, the firm will produce all y units of output using y over 3 units of factor 2. If, on the other hand, production with factor 1 is cheaper, then the firm uses no factor 2. And in the case in the middle, where the isoquant line is on top of the isocost, the firm can use any combination that they choose. Any cost is cost minimizing. Imperfect substitutes, we'll consider the Cobb-Douglas case. So a Cobb-Douglas production function is multiplicative. So here we are multiplying labor and capital. And you recall back in the theory of the consumer that if I want to find in this case, cost minimizing combination of capital and labor, I will set the slope of the isocost line equal to the slope of the isoquant. The isocost line, the slope is easy to determine. We've done it before. The slope of the isoquant we can derive by using our favorite theorem from chapter 4, the ratio of the marginal products. And you find that in this particular case, the slope of the isoquant is minus k over L. If I set the slopes equal, I get this relationship that if the firm is minimizing costs, L will equal 4k. So in other words, the firm needs 4 units of labor for each unit of capital. I can substitute that relationship into the production function and find out the cost minimizing quantities of capital and labor, given I want to produce an output level of 50. Now you might remember back in the theory of the consumer, we had this wonderful closed form result which we called the exponent rule. It allowed us, when we had Cobb-Douglas preferences, to solve once for the demand for commodity 1 and commodity 2. It was the the sort of problem we could solve once and then apply this general solution universally. And happily, that result also holds for the theory of the firm. The exponent rule applies. So from setting the slope of the isocost line in general equal to the slope of the isoquant in general, we can derive the exponent rule. We can see that alpha over alpha plus beta is the proportion of total cost that represents expenditures on factor 1, and beta over alpha plus beta is the proportion of total cost that is taken by expenditures on factor 2. We can rearrange these expressions to come up with factor demands for factor 1 and factor 2, much like we did before. Now, in chapter 7, we had revealed preference, and we had warp and SARP, and then in the last chapter, we had the weak axiom of profit maximization, WAPM. Today, we get to do WACM, the weak axiom of cost minimization. And thankfully, Hal ends here. There is no SACM to follow WACM. WACM is the end of the line. So the way that Hal describes WACM is, remember, this is the case of like Warren Buffett, the super investor who spends all his work hours pouring through the statements of firms. End-of-year reports, quarterly reports. He looks at the different quantities of inputs that the firm uses. He pores over their balance sheet. So he looks at costs and output levels. Buffett doesn't know what the firm's actual production function is, but from looking at these financials, these disclosures, he can come up with a reasonably good idea of whether the firm is being run in a profit maximizing or cost minimizing fashion. So in this case, we don't know what the production function is, we don't know what the isoquant is, but the isocost lines will enable us to come up with a lower bound for the isoquant. So the necessary conditions, if the firm is observed to produce the same quantity of output in each period over a number of periods, and it is using the cost minimizing choice in each period, then we get a diagram that looks like on the left. And then at the bottom of the slide, we have the mathematical representation of WACM. Delta omega 1 delta x1 plus delta omega 2 times delta x2 is less than or equal to 0. That's the mathematical representation of WACM. And I'll explain in a couple more slides what that means at an intuitive level. Here's an example of a violation of WACM. So what I can say then is that when the bundle on the left, so the firm is using 4 units of x1 and 8 units of x2, and then I've placed an isocost line through that point, you'll notice that the second point with 8 units of x1 and 4 units of x2, it's actually cheaper because it falls in the interior of the budget set. So the firm is using a more expensive combination of inputs than they had to, and that's a violation of WACM. Okay, and likewise, when they use that second combination of inputs on the right, the combination on the left is in the interior of the set. So in both time periods, the firm is not choosing the cost minimizing technologically feasible combination of inputs. So here we have the numerical values in the table, and we could combine them together in a matrix much like we did with warp back in the theory of the consumer. So we have prices on the horizontal or on the rows, we have input levels in the columns, and you'll notice that the first input bundle costs $100 when it was chosen, but the second input bundle, which is also technologically feasible, would have cost $80. So the firm is choosing a more expensive bundle of inputs to produce the desired level of output than they really had to. They're not minimizing costs. Now, to revisit Wacom and state very carefully what it tells us and what it does not, Varian started with the assumption that the firm was minimizing costs. And from that assumption of cost minimization, he derived Wacom. Delta omega 1 delta x1 plus delta omega 2 delta x2 is less than or equal to 0. Or in words, a cost minimizing firm will never substitute into a more expensive factor of production. So suppose we have a situation where in the next time period, factor 1 becomes more expensive, but the price of factor 2 is unchanged. Okay, so if they produce the same amount of output next time period as they do this time period, factor 1 becomes more expensive, but factor 2 costs the same. What Wacom is telling us is that a well-run cost-minimizing firm will never choose to use more of factor 1 now that it has become more expensive. And that's just common sense, right? It's evident. Okay. So what we know then is that if Wacom is not, okay, so back up, Varian assumed cost minimizing behavior and showed that Wacom is satisfied. If Wacom is not satisfied, then we can conclude the firm is not minimizing costs. However, if Wacom is satisfied, we can't really imply anything from that. The firm may be minimizing costs, they might not. We're actually uncertain, and I'm going to show this numerically in just a second. But let me first review for you the rules of logic. So if cost minimization implies Wacom, then not cost minimization if cost minimization implies Wacom, then not Wacom implies not cost minimization. Wacom, however, does not imply anything in and of itself. What this means literally is that it is possible to come up with numeric examples of behavior that satisfies Wacom but does not minimize costs. So I have come up with a numeric example to my immediate left. So we have prices in time period 1 and time period 2, and then input bundles. So if I look at the mathematical explanation of or description of Wacom, you'll notice that going from time period 1 to time period 2, factor 1 has become cheaper. The firm is observed to use more factor 1, which has become cheaper. Factor 2 has become more expensive, and the firm uses less of it. Those are both reasonable things to do that seem to be well thought out. However, if I price out bundle 1 in, so looking at the first row, bundle 1 costs $144 at the time period 1 prices. Bundle 2 is more expensive, so in the first time period, the firm's behavior fulfilled Wacom. But then in the second time period, it turns out that the first time period bundle is actually cheaper than the one that was used. So even though this behavior fulfills the mathematical definition of Wacom with the deltas, you can show that Wacom does not necessarily imply cost minimization. Okay, so be careful. Now, we're going to revisit returns to scale. And again, we have a Cobb-Douglas production function. And if I scale both factor 1 and factor 2 up by this amount t and then factor out, you recall this result that we reviewed back in chapter 19, that for a Cobb-Douglas production function, a multiplicative production function, if the exponents sum to greater than 1, we have increasing returns to scale. If they sum exactly to 1, we have constant returns to scale. And if they add up to something less than 1, we have decreasing returns to scale. Returns to scale have this very interesting implication on average cost, or the cost per unit consumed. So what we can say then, average costs are total costs divided by the quantity of output produced. And if I have increasing returns to scale, what I can say then is costs, if I doubled my inputs, what I know is that if I double my inputs, my cost exactly doubles, but my output more than doubles. So when increasing returns to scale are in effect, output grows more rapidly than costs. What this implies then is that the average cost curve is going to be decreasing, meaning the per unit cost becomes smaller as the firm becomes larger. Larger firms are more efficient. Constant returns to scale have constant average costs because costs and output grow at the same rate. The per unit cost is the same for a small firm versus a large firm. Whereas for decreasing returns to scale, costs grow more rapidly than output level, and the larger a firm is, the larger the per unit cost is. Larger firms are less efficient. Okay. So, in the short run, capital is fixed. Everything else varies with output. In the long run, we're all dead. Everything is variable, including you. And in the long run, you can have what Hal defines in his textbook as quasi-fixed costs. Quasi-fixed costs would be an example of costs that do not change in output, but can be avoided if the firm shuts down. So, for instance, in the short run, capital costs would represent fixed costs, whereas in the long run, you have costs that are still avoidable, but they don't change in output. One classic example might be lights in a factory or lights in a classroom. Right? So, regardless of whether my micro class has 5 people enrolled or the room is filled and we have 40 people in class, the cost to Baylor of turning all the lights on remains the same. It can be avoided if my class were not held. Right? And finally, sunk costs are fixed costs that are not recoverable. So it would be a cost that doesn't change in output, but when the firm liquidates, it can't be sold to an alternate use. It's basically money down a rat hole. Okay. So quiz problems. Quiz question 1. Let Nadine have a production function where the two factors are perfect substitutes. Factor prices are 20 for 1, 2 for 2. How much would it cost for her to produce 20 units of output? Well, she can produce output using all of one and none of the other. So what we need to do is find out what it would cost Nadine to produce using each factor, factor 1 and then factor 2, and we'll choose the method of production that has lowest per unit cost. So she can produce 20 units of output with 4 units of factor 1 or 20 units of factor 2. 4 units of factor 1 cost $80. 20 units of factor 2 cost $40. She will want to produce using factor 2 at a cost of $40. Two firms, wickedly efficient widgets and wildly nepotistic widgets, both produce with the same Cobb-Douglas production function, where we have capital and labor. We have costs for capital and labor. The efficient firm produces 10 widgets per week using the cost minimizing combination. The nepotistic firm uses twice as much labor as the efficient firm. And the question is, how much larger is the nepotistic firm's total costs than the efficient firm? So we can do this by applying the exponent rule. That would be the simple way of doing so. Given the production function, what we know is that the firm, half of the firm's total costs will be capital, half will be labor. Given the rental cost of capital and the wage rate are both 1, if omega L equals RK, omega and R are equivalent, then L equals K. The efficient firm is going to use the same amount of capital and labor. If they're going to produce 10 units of output, K to the 1/2, L to the 1/2 equals 10 is the same as squaring both sides. K times L is 100. If K is equal to L, I can substitute in L for K. Now I get L squared is 100 and L is 10. So the efficient firm uses 10 units of labor and 10 units of capital at $1 each for a total cost of 20. The nepotistic firm uses twice as much labor. So if the efficient firm used 10 units of labor, the nepotistic firm uses 20. And to produce 100 units of output, 10 units of output, K to the 1/2, L to the 1/2 equals 10. It's equivalent to saying K times L is 100. If L is 20, the efficient quantity of K is now 5. So the nepotistic firm's total costs are 25. So there's an additional $5 of cost for the nepotistic firm that hires too much labor. So that does it for Chapter 21.